I'm Hassan Altor. In this presentation, I will explain our real-time electric vehicle dashboard and ADAS warning system. The project simulates an automotive embedded system using the STM32F103 Blue Pill, PixemLab UART communication, and a Python dashboard. The purpose is to monitor EV parameters and detect safety conditions such as collision risks, blind spots, and faults in real time. I will follow a clear structure. First, I will introduce the problem and the objective. Then I will explain the architecture and the firmware modules. After that, I will show how the simulation is prepared using STM32 Cube IDE, PixemLab, and the Python dashboard. Finally, I will walk through the live test scenario, including the normal driving, collision, warning, blind spot, detection, fault triggering, and recovery. The problem is that an electric vehicle produces many real-time values. The engineer needs to monitor the vehicle performance and also safety conditions at the same time. In our project, the solution is to build a complete simulated EV ADAS system. The STM32 reads sensors, computes vehicle behavior, detects warnings and faults, then sends the result to a Python dashboard. The main tools are STM32 Cube IDE, PixemLab, and Python. STM32 Cube IDE is used for pin configuration and firmware development. PixemLab replaces the physical hardware and gives us the blue pill board with virtual sensors. UART connects the simulated microcontroller to the terminal or the Python dashboard. Python is used to visualize the received telemetry. The architecture can be summarized as a pipeline. At, at the first stage, PixemLab simulates the sensors. At the second stage, the STM32 processes the sensor data. At the third stage, it sends the processed values using UART. At the final stage, the Python dashboard displays everything in real time. This separation makes the project easier to understand and debug. This slide shows the main STM32 pin mapping. PA0 to PA3 are analog inputs. PA9 and PA10 are used for USART1. PB0 to PB5 are used for the three ultrasonic sensors. PB8 to PB11 are output LEDs for collision, blind spot, and fault indication. PA8 is used for TIM1 channel 1 PWM, which can represent the motor command or safety cutout. The timers are important because this is a real-time embedded project. TIM2 is configured as a microsecond counter, so the ultrasonic echo duration can be measured accurately. TIM3 creates a slower periodic task around every 100 milliseconds for reading sensors, updating ADS, and sending telemetry. TIM1 is used for the PWM or motor control output. The, A- the ADC module converts analog values from potentiometers into digital values from 0 to 4095. These raw values are not useful alone, so we scale them into engineering units. Accelerator and brake become percentages, SOC becomes battery percentage, motor temperature becomes a temperature value. These values are then passed to the EV control module. The EV control module is responsible for calculating the vehicle behavior. When the accelerator increases, the firmware increases torque and speed. When brake is applied, the system can activate regenerative braking, which produces negative torque and slows the vehicle. The module also estimates SOC and range. Drive modes drive modes change how strongly the vehicle responds to the same accelerator input. The HCSR04 sensor works by sending a short trigger pulse and measuring how long the echo pin stays high. TIM2 measures this echo duration in microseconds. The distance is calculated by multiplying the pulse time by the speed of sound and dividing by 2 because the sound travels to the obstacle and back. In the final system, we use one front sensor and two side sensors. The ADAS module converts raw distances and speed into clear alarm levels. The front sensor is used for collision warning and time-to-time collision calculation. The side sensors are used for blind spot detection. Alarm priority is important because the system must know which warning is most urgent. Critical collision has the highest priority. The vehicle state machine makes the behavior deterministic. The vehicle starts in park, moves to ready, then driving. When braking is applied, it can go into regenerative braking if a dangerous condition occurs, The fault manager moves the system to fault. In the fault state, the torque is disabled, the system is placed in a safer condition. UART is used in two ways. First, it streams telemetry to the terminal and the Python dashboard. The firmware prints two structured lines, one for EV data and one for ADAS and fault data. Second, the UART shell allows diagnostic commands such as checking status, changing mode, injecting faults, and clearing faults. The Python dashboard makes the system easy to understand visually. It receives the UART data, parses the values, and updates the display. The dashboard includes a speedometer, battery bar, speed trend graph, EV metrics, and an ADAS bird eye view. During the demo, this dashboard is the best place to show how the embedded decision appear in real time. Now I start the simulation preparation from STM32Cube IDE. I open the final project and the .ioc file. I show the pin configuration PA0 to PA3 for ADC, PA9 and PA10 for UART, PP0 to PP5 for ultrasonic sensors, and PP8 to PP11 for the alarm LEDs. I also show the timer configuration. After that, I build the project and confirm that the firmware is generated successfully with no errors. The output file will be loaded into Pixim Lab 32 Cube IDE project. The code is organized inside core SRC and core INC. I divide the project into separate modules instead of writing everything in main.c. We have evcontrol.c, ads.c, fault.c, ultrasonic.c, UART shell.c, main.c. Each module has a specific responsibility which makes the project easier to debug and explain. In main.c, I include the project modules and create the main handles for EV control, ADAS, and fault handling. During initialization, the firmware initializes the EV model, ADAS module, fault manager, ultrasonic driver, PWM, timers, and UART shell. In the main loop, the firmware first checks if any UART command was received, then it processes shell commands. After that, every 100 milliseconds, the system reads, sensors, and updates the logic. This sequence is important. First, ADC values are read. Then the EV model is updated. Then ultrasonic distances are read. After that, the ADS logic is updated, faults are checked, and the status is printed through UART. This printed status is the same data used by the Python dashboard. In evcontrol.c, this file contains the EV model. It reads the accelerator, brake, SOC, and temperature values. Then it calculates the torque and speed. When the accelerator is high and the brake is low, torque becomes positive. When the brake is high, torque is reduced. If a fault is active, the torque can be forced to zero for safety. In ultrasonic.c, this model controls the HCSR04 ultrasonic sensors. It sends the trigger pulse, waits for the echo signal, measures the echo time, and converts it into distance. The measured distance are later used by the ADAS module. In ADAS.c, this file contains the ADAS decision logic. It checks front distances and time to collision for collision warning. It also checks the left and right distances for blind spot detection. Based on these values, it sets collision level, blind spot status, and alarm priority. In fault.c, this is the fault manager. It checks low SOC, motor over temperature, and critical collision. Each condition activates a fault flag. For example, as a hexadecimal 0x01 is temperature fault and 0x02 is low SOC and 0x04 is collision fault. In UART shell.c, this file handles UART communication. It sends the startup message, receives comments, and prints system.state. The dashboard depends on this UART format, so the output must remain consistent. Now I'll move to the live simulation and dashboard. After building the firmware, I move to PiximLab. I select the blue pill board and load the generative firmware. Then I connect the virtual components. 4 potentiometer simulates the accelerator, brake, SOC, and motor temperature. 3 ultrasonic sensors simulate the front, left, and right distances. 4 LEDs represent collision, left blind spot, right blind spot, and fault indicators. The virtual terminal is connected to USART1 for UART output. Before starting Before starting the dashboard, I first verify the UART output in the terminal. I check that the EV frame and the ADAS frame are printed correctly. Once the text output is correct, I open the Python dashboard. If I don't know the compose, I check the serial port used by the Pixel Lab or the virtual compare. Then I run the dashboard command and confirm that the visual panels update in the read time. Now we have the Pixel Lab. First of all, we load the bin file, the binary file from the STM32 to the Pixel Lab to have it. Now we have the blue pill board and the other uh, spare parts. We have four potentiometer sensors and three ultrasonic sensors. The four potentiometer sensors are for the accelerator, brake, state of charge SOC, and the motor temperature. And the three ultrasonic sensors are for the distances between our car, first sensor to the front car, and the two other sensors are for the uh, left sided car, and the third ultrasonic sensor is for the uh, right sided car. The normal state, the battery is 98%, the alarm is none, and the fault is 0. Now we will change in the four potentiometers and the three ultrasonic sensors to see how the Python dashboard it will be changing here. We increase the acceleration uh, till the speed in the Python dashboard. It will be changing its number now till 14 kilometer hour, 24 kilometer hour, and will be changed. And as we see, the distance is changing also between the two cars. Now, if we increase the braking sensor, we will see also how it will affect the uh, speed on the dashboard, and also we decrease the acceleration sensor. The speed will decrease now uh, very to very low number. And now we decrease the braking system till 0, the braking sensor. Now the SOC sensor state of charge to see how the battery on the dashboard will change. Now we see the battery percentage, how it becomes 0%, and we see how the alarm and fault turns red, and the fault is 0x02, which is the fault corresponding to the battery percentage. Now if we increase it, the battery percentage will change and increase to 94, for example, percent. Now the motor temperature sensor, if we increase it very high, also will have the alarm which turns red, and the fault which is 0x01, which is the fault corresponding to the motor temperature. Now we decrease it till 0, and the alarm and fault uh, return to the normal state. Now the ultrasonic sensor, which is that for the distance, which will appear on the distance between the two cars, with the our car to the front car. We decrease the sensor, and the distance between the two cars affected and will be decreased. And as we see here in the dashboard. Now for the two other sensors, add the first sensor, but uh, for the left-sided and the right-sided. As for not to forget, the alarm and the fault shows critical because the distance are too near to between the cars, and the fault is 0x04.